Alrighty. Good morning, everyone. My name is Robert Smith, and I'm a graduate student at the University of Tennessee at Chattanooga. And I'm going to be presenting today concerning subgrid modeling of reaction rate using a multi-scale strategy for large eddy simulation of turbulent combustion. I work under the supervision of Dr. Ratish Ranjan, and I am as a member of the Fluids and Combustion Modeling Group. And specifically for this paper, I had the help of an extra advisor, Dr. Trevor Elliott. So I want to thank him for that as well. Alrighty, let's get into it. So a quick little introduction. Turbulent premixed combustion can be observed in a multitude of practical applications. Practical application devices such as internal combustion engines, swirl combustors, spray combustors, aero and automotive engines, and what have you. Turbulent combustion is the interplay of several processes, and here we define three main categories of such processes. First up, we have large scale, which can be characterized by stretching and or wrinkling of the flame surface or scalar surface. Next, we have small scale, which includes turbulent mixing, molecular mixing, chemical reactions, things of that nature. Finally, we have something of a middleman. We have small to large scale coupling. And the one process that we're really interested in here is going to be volumetric expansion. Some of the challenges that we must address when performing subgrid modeling include, but are not limited to, the handling of multimodal burning, robustness and efficiency of the closures, the ability to account for finite rate kinetic effects, the effects of compressibility, and so on and so forth. But those are the main ones we're worried about. All right, so the objectives of this study were to develop a dual grid two-scale strategy for modeling of turbulent combustion using the linear eddy model as a base, and then we're also going to assess its performance for premixed combustion. Okay, so the compressible LES equations are obtained by spatially filtering the Navier-Stokes equations using a top hat Favre filter, which is appropriate for finite volume schemes. Here, all of the subgrid terms, especially in that last equation, which is for the filtered scalar transport, all the terms that are denoted by the superscript SGS require closures, and we're going to focus primarily on the filtered scalar transport equation, specifically the filtered reaction rate term for each species, as we can see on the bottom, which is that omega sub k. Okay, so now we're going to talk for a moment about the formulation of LEMLES, which stands for the linear eddy model in large eddy simulation. This model, or this is the model that RRLES is heavily based on. Is actually the reason that RRLES is a thing. And dare I say RRLES is an improvement over this formulation. So here we have the exact species transport equation in a modified form, and right underneath it is the decomposition of the instantaneous velocity field. So LEMLES uses a two-scale decomposition in order to solve for scalars, in which the first equation shown is rewritten as a two-step problem. However, the implementation of step 2 in LEMLES is distinctively different to the conventional finite volume approach, since it employs a Lagrangian transport approach. This transport is implemented using a splicing, big air quotes on that, a splicing algorithm, which was designed primarily for high Reynolds number statistically stationary flames where the turbulent mixing is way more intense than the molecular mixing at the large scales. As a result, this approach does not account for molecular diffusion across the LES cell faces, even though step 1 accounts for the SGS molecular diffusion processes. We don't really see this limitation a whole lot in highly turbulent flows. And you guys are going to get a chance to look at that or experience that, dare I say, here later on when we get to the results. So we've got two cases. One is a low turbulence case and one is a high turbulence case. So you'll get to see that. And it's actually pretty cool. These limitations are very well known and are of pretty good concern, as they do not asymptotically achieve laminar or even the DNS limits as originally implemented, only as a true LES SGS closure. The effective heat release is also included within the SGS model by carrying out an explicit expansion of the 1D domain, ensuring proper mass conservation. Finally, in LEMLES, after the completion of the two-step process, the filtered species field, which is necessary in the LES equations, is obtained from the subgrid 1D LEM fields. Some of the key challenges here are the lack of numerical diffusion due to that splicing algorithm, the ignoring of the large-scale laminar diffusion, and grid convergence. So now that we've talked about LEMLES, now we're going to talk about RRLES, which is the modified version. So RRLES stands for reaction rate large eddy simulation. In this model, the species transport equation is used as in most other conventional LES, except that the term S sub k is modeled differently. The subgrid scalar flux, or the YKISGS, now requires a closure, and a conventional gradient hypothesis is used, as this is seen in this first equation, where the eddy diffusivity, or d sub t, is obtained from the eddy viscosity. A major disadvantage here is that in the turbulent flows where SGS closure is necessary, only gradient transport is allowed, and hence counter gradient effects cannot be accounted for, unlike in LEMLES. With this closure for the subgrid scalar flux, the species transport equation can be arranged as is seen here. So the key differences between RRLES and LEMLES are observable primarily as the replacement of step 2 in LEMLES, which is the filtering of the species mass fractions, by the estimation of S sub k from RRLES. The reconstruction of the subgrid field is the key issue in RRLES. At present, the gradient-based reconstruction is summarized by this first equation, where R is the restrictor operator or restriction operator that does a conservative filtering of the fine grid, indicated by delta, to the coarse grid, indicated by 2 delta. And we do this to initialize, or it does this to initialize the LEM fields. The filtered reaction rate within the 1D LEM is computed using that second equation there, where delta V sub n is the volume of the nth cell. Since the 1D LEM equations are solved at the subgrid level, the effects of the subgrid molecular diffusion and turbulent stirring, as in step 1 of LEMLES, are implicitly included here. And we also are using a local dual grid strategy, where the LEM equations are solved on a local coarse cell, as we can see in this first top figure. And the reason we do this is strictly for improved performance. As everyone in CFD knows, with a coarser grid, things run faster. And we all like to have our answers as quickly as we can, because that means we get to tell whether we screwed it up or not. But as I mentioned earlier, this does require a consistent restriction operation for resolved LES quantities needed by LEM. All right, so now that we've kind of got some background into the solvers that we're using and what we're doing, so let's go over the actual numerical methodology. So all the simulations that we did in this study were performed using a in-house, fully compressible, multi-species Navier-Stokes solver called AVF Leslie. It was developed by my advisor while he was doing his postdoc at Georgia Tech at the CCL there. And we are also going to be using a second-order accurate McCormick scheme, which is very well known for our spatial discretization. For our time integration, it is also second-order explicit. For our finite rate kinetics here, we're using a moderately complex 4-step and 8-species methane air chemistry. It's not crazy, but it's enough to get the job done. And we also used a mixture average transport while making the thermally perfect gas assumption. For our boundary conditions, we used a characteristic inflow-outflow in the X direction and periodic in the Y and Z. And on the next slide, you'll actually see the configuration. For our closures, we are using a momentum and energy flux with dynamic eddy viscosity based on transport equations for the SGS kinetic energy. And of course, we are going to be using LEMLES and RRLES and then comparing the results. And actually, an added function of this report or this paper was, and we'll see that later at the end of the results, is we're going to be comparing the dual grid strategy for RRLES versus the single grid. And so that kind of adds an extra layer of complexity to this study. All right, so here's our setup. It is a fully 3D, freely propagating turbulent premixed methane air flame And we did two different turbulence conditions. So we have case A and case B. For our flame conditions, we used an equivalence ratio of 0.7. So we're running, lean as most practical application devices do. We're using a reference pressure of 570 Kelvin and a reference pressure of 1 atmosphere. So the initialization of the turbulence is based on a laminar solution, which we then impose on background turbulent flow. We use a software called turbulent to generate that, and we input the parameters from the study, derive all of either it's going to be reported or we derive the quantities ourselves, such as integral flame length, turbulent flame speed, laminar flame speed, things like that. And it will generate the turbulent file for us. The computational domain, the cube is physically very small. It's 5.5 millimeters cubed, very, very small, which makes the grid sizes very appropriate here. So for case A, the DNS, of course, is there. It's around 8 million cells. Case A for the LEM and RRLES runs were about 262,000 cells. Case B for the DNS was a whopping 18.6 million cells. And for the LEM and RRLES for case B, we did around 885,000 cells. And you can also see in the lower diagram that we have each case plotted in a turbulent premixed regime diagram. And of course, A is in the thin reaction zone, B is in the distributed burning broken reaction zone. And of course, in that top figure, you can actually see the boundary conditions. So we have periodic and we have the inflow and the out. All right, so the figures included here show the instantaneous structure of the flame brush obtained from the DNS of both flames. So we have case A, case B. The samplings were done at 3 eddy turnover time. So we can observe intense wrinkling and stretching of the initially planar flame surface by the turbulent eddies. The effect of the heat release and the associated thermal expansion across the flame is apparent in terms of the increase in the overall length scale associated with the protruding structures on the reactants and the product side. A typical role of the turbulent eddy is to transport pockets of cold reactants toward the reaction zone, which sustains the flame. As expected, the flame structure is continuous, thus precluding any local extinction. The width of the flame brush varies spatially due to the straining effect of the large-scale eddies, and the increased flame surface area results in an increased fuel consumption rate. The flame structure and its characteristics were assessed using this progress variable C, which is essentially just a ratio of the stoichiometric fuel level, and then we also have fuel in the unburned and burned regions, which are indicated by the U and B. Obviously, the highest value you can get for that will be 1, the lowest value is 0. So, and as we can see, we have 1 and 0, and then everything in between. Like I said, these were run for 3 eddy turnover times, where the initial value, or T naught, is indicated as the integral length scale over the velocity, or integral length scale over the velocity length scale. Alrighty, so the figures shown here compare the flame structure from the simulated cases. The wrinkling and stretching of the flame is predicted by all closures in a very consistent manner. We see an increase in wrinkling along with enhanced transport from heat from the reaction zone from case A to case B is qualitatively captured by all closures. All simulations show continuous flame structure with no sign of local distinction for these conditions, which you wouldn't see anyways. Qualitatively, there are some noticeable differences between the different closures. Specifically, DNS and RRLES show more fine-grained features compared to the LEM-LES formulations. This is particularly apparent for case B. As we can see, LEM-LES on the far right, not a bad profile. Get to RRLES, looks better, and of course DNS looks the best because it's the finest grid. Alrighty, so here we have spatially averaged flame structures for progress variable versus non-dimensionalized distance. We have heat release rate and H2 mass fraction, which is hydrogen, which is an intermediate species here. In all cases, we observe a pretty good agreement of the results with the DNS data, and all of the methods are able to capture the global flame structure, except in case A, where naturally LEMLES underpredicts the absolute fool. It doesn't do bad for progress variable versus non-dimensionalized X, but it's just so bad for heat release rate and hydrogen mass fraction. And that's what we expected to see. So we're not disappointed. For once, we're not disappointed to see a pretty bad result. But case B, higher turbulence, it picks back up, and it actually does a really good job. They all three do a really, really good job. Of course, you see that LEMLES still underpredicts a little bit, and RRLES overpredicts. But overall, in the scheme of things, they're still pretty similar. All right, so here you have the spatially averaged flame structures for the single versus dual grid. What you can see here is that they both do a very good job, especially for progress variable versus X. We see that although single underpredicts and RRLES or the dual overpredicts, the overprediction is less of magnitude than the underprediction. And of course, especially for the progress variable, and of course we see for heat release rate and the hydrogen mass fraction that although the profiles are very good across the board, RRLES dual does do a better job. So here we have the conditionally averaged flame structure. So the conditional variation of the filtered reaction rate for temperature, heat release, and product mass fraction is shown. So the same quantities that we did for spatial. The peak location is shifted towards a higher value of progress variable for all cases. The improved predictions by the RRLES formulation are noticeable in all the cases where we can observe a very good agreement with DNS data. The asymptotic behavior of RRLES is again evident here, as we can observe that its predictions approach DNS and laminar flamelet in case A, while the level of turbulence is small or relatively low. These predictions by the various closures highlight their abilities and limitations. The unphysical results predicted by LEMLES in case A demonstrate the limitations of its formulation, as I've mentioned more than once, when the local flow conditions tend to have a very low subgrid scale turbulence. In case B, we see that RRLES and LEMLES are similar. They're more similar than they are for case A, but we tend to see this overprediction from RRLES, and we also see, at least for hydrogen mass fraction, LEMLES does a very good job, and RRLES overpredicts just a tad bit. But overall, very good results. And of course, we have the conditionally averaged flame structures for the single versus dual. And one thing that we didn't really expect to see here was the single grid doing such a good job. As you can see by the blue dots, on top of that red line, it pretty much follows the DNS profiles perfectly, which we didn't expect to see. What we think might have happened, I mean, I'm not saying any of these did a bad job here, but I'm saying that we think that one of the possible sources of this potential error would be the averaging method we use. So we did conditional averaging using bin averaging for condition. So for like each value of progress variable, we averaged all of the values of, say, temperature at that point and did that across the spectrum. So there could have been something wrong with the script that I used to do this averaging and make these plots, but that's something we definitely plan on looking into later. So quick little summary. So we looked into RRLES, the dual grid and single grid closure for the filtered reaction rate term. We know that it's relying on an LEM assessed in this study. But what we did is we compared the two. We compared single grid, dual grid RRLES versus each other, and then we just compared the dual grid RRLES versus the LEMLES. As we know, LEMLES, very good solver, but RRLES does address some of the challenges faced by it. This leads to a much more modular strategy for subgrid modeling of turbulent combustion. The freely propagating methane air turbulent premixed flame is considered two cases, A, B, low turbulence, high turbulence. And what we see is that RRLES is able to capture spatial and statistical features of both flames. And as expected, the LEMLES performs better at high turbulence. So some of the future directions, we're looking into the closure of other terms using information from the subgrid LEM. And then we also want assess the performance of other canonical configurations. All right, I think that's all I've got. Thank you very much, and I hope you enjoyed it.